All right, welcome everybody to the last day of school. I know it's been kind of a long road. This year has been a strange year to say the least. I don't know. I think it started off all right. Really, you're gonna do this to me today, computer? Okay, well, today, I guess to pull this up like this, we're going to be going through water use and management. So our outline, which I can click through, we're going to talk about the hydrologic cycle, so major water compartments. So remember the term sink and source, water availability and use, types of, I just realized that major water compartments and sink and source. I didn't mean that as like a sink in your house, but sink and source, like where something comes from and where something ends up at. So back to it, types of water use, freshwater shortages, depleting groundwater is an issue that we're going to discuss, increasing water supplies, water management, conservation, and price mechanisms. So looking at water resources, as you can see in this picture, it does have some water in it. So water, liquid or solid, covers more than 90% of the world's surfaces. By volume of the earth, it is not a major component just because there's so much rock, but when it comes to the crust, it is a major component of the earth. I mean, looking at this picture, you could just see the amount of water that's available here. On top of that, it's like, well, you're taking a snapshot of this, you're not taking into account like the Great Plains, which there's very little water. But then I would counter that with look at the North Pole, where it's just a gigantic, it's frozen, yes, but it is a gigantic thing of water. There's more than 370 billion gallons of water, which is enough to fill up 3 swimming pools, if I did my math correctly. So looking at the hydrological cycle, this describes the circulation of water as it evaporates from land, water, and organisms. The big one is transpiration from plants. Plants usually only open their stomata at night in order to allow water vapor out, or to minimize the amount of water vapor that's lost through transpiration. That then enters the atmosphere, and then it condenses and precipitates back to the Earth's surface in rain and snow. Then it moves underground by infiltration or percolation or overland runoff into rivers, lakes, and seas. So remember, it's percolation when it goes through the soil. It is runoff when it's above the soil. So here's a really, really good picture of it. So here's a comet for some reason. I guess it's one of those days. So let's start in the ocean, major sink. So you end up with evaporation, brings water vapor up, which then condenses down. Now notice that not all is accounted for when it comes to evaporation and precipitation. Think of this as math, all right? So if you have this much, so 425,000 cubic kilometers minus 385,000 kilometers, and then you're basically just doing math this whole way. So then you have 40,000 kilometers that is transported on shore. Then you have comets are made out of rock and ice. You have snow and ice on top of mountains, and then water vapor in the atmosphere. Condensation happens. You end up with precipitation, infiltration into groundwater, or percolation. You have this lake, which again is another source for evaporation and transportation. Then you have runoff, which causes the flow of water on the Earth's surface, and then the flow of water and groundwater being percolation. So you can see that all of this adds up. So how is new water added? Well, as a comet comes in, it adds new water. It's not a whole lot, but it is a source that over the millions of years that the Earth has been around, then it is a source you have to take into account. So solar energy drives the hydrological cycle by evaporating water or surface water, and evaporation is changing from a liquid to a vapor below its boiling point. Sublimation is changing water between solids and gaseous states without ever becoming a liquid. This tends to be a little more common in something like dry ice. So freezer burn is an example of this. Hydrological cycle, humidity, or the amount of water vapor in the air. I mean, we've all heard about humidity. It's just the saturation level, 0 being no water in the atmosphere, 100% being full saturation of the atmosphere. Once you hit 101%, or once you go over 100%, then that's when you start to end up with rain. The saturation point is when a volume of air contains as much water vapor as it can hold at a given temperature. So that is, think about a sponge or a paper towel, right? If you have a water dropper and you start adding drops of water to a paper towel, eventually you're going to hit a point where as you add another drop, it can't hold anymore, and it's going to have to release a drop of water in order to hold that. So that is saturation point. Relative humidity is the amount of water vapor in the air expressed as a percentage of that maximum volume that can be held at that temperature. Notice that's the key, held at that temperature. As the temperature changes, the humidity or the saturation point will vary. So that's why it's done off of 0 to 100%. Because if you were to do it, like, let's say it was on a scale of, like, let's say 0 micrograms per liter compared to like 10 micrograms per liter. Well, 10 micrograms per liter might be saturation point in really cool air, but then you look at something like really warm air, it might be closer to like 15. This was an issue when I was a diver, and when you're a diver, one of the things that you have to worry about quite a bit is water temperature, not just for comfort reasons, but because if you are a saturation diver, you literally saturate your tissues with the maximum amount of nitrogen, or in the case of trimix, helium, that your body can store within those tissues. And so as the temperature changes, the amount of helium your tissues can hold will vary a little bit. So if you're cold, then it's going to start to force some of that, or it's going to hold more gas inside of your tissues. And then instantly, once you enter your dive chamber and it's warmer, then those gases are going to start to escape a little bit. And therefore, that gas has to go somewhere, and that's when it can lead to dive injuries. So relative humidity or looking at the temperature is important when calculating that relative humidity. The dew point. You probably see this if you've ever watched a weather forecast, but the dew point is a temperature at which condensation occurs for a given amount of water. Condensation nuclei is a tiny particles that facilitate condensation, or the formation of a droplet. So smoke, dust, sea salt, spores, anything that causes two water molecules to start to come together and compound that. So mountains act as cloud formers and rain catchers. You'll sometimes hear about the California winds. This is the same exact thing. These winds kind of bounce off of the mountains, causing air movement. So wind sweeps up the windward side of a mountain, pressure decrease, and the air cools. Eventually, saturation point is reached and moisture in the air condenses. And rain falls on top of the mountains. Cool, dry air descends and warms, absorbing moisture from other sources. This is called a rain shadow. I'm trying to think of an example of this, but I'm kind of blanking on it. So this is what it looks like. So you have this moisture-laden air. So moist air comes in. These winds kind of gather it in. It cools as it rises, and because it's getting colder, it's the relative humidity, or the amount of, or I'm sorry, not the relative humidity, the amount of humidity that it can hold, or the amount of moisture it can hold, decreases, which means it's going to start to cause rain, and then this air will then start to sink down, and it's drier, leading to this rain shadow. So rain shadow, you could see that it gets 40.46 meters per year, so 46 centimeters per year, compared to 11.8 meters per year of rain. Desert belts. Evaporation is nearest or is highest near the equator, as direct sunlight produces the greatest heat budget. Air at the equator rises, cools, and falls as rain, forming rainforests at the equator. Cooler, drier air descends along the Tropic of Cancer and Tropic of Capricorn. These are kind of the tropics of Cancer and Capricorn are these areas where when the Earth tilts, that is the maximum area of sunlight. So if you ever see a map that has an S written on it, that's the location of the sun at that time. Where it's directly above. And so that is the spot of perfect solar noon. And what will happen is the tropics of Cancer and Capricorn are the furthest north and furthest south that that'll ever end up. Causes evaporative losses and creates deserts. So you can see here where precipitation is, you end up with these kind of desert regions. So this is 0, right here. If you really want to see this, look up anyone who is, go to aprs.fi, which is a website for the automated packet reporting system, which is a ham radio or amateur radio positional reporting service that you can use to send messages. But a lot of times people send their signal, and if they don't know how to set it up correctly, it'll default their signal to either 00 or it'll default it to 50. And so you have a ton of people that are located all the way down in south of England, and you also have a ton of people that are located right here. And it's so weird just to see the cluster of people that are grouped right there. It's like thousands of stations. Balancing the water budget. Oceans account for 86% of total evaporation. 90% of water evaporated from the ocean falls back on the oceans as it rains. This is just because of having such a large, the oceans take up a large amount of the surface area. There's this little girl right outside my window who's like fighting with this umbrella as hard as possible, even though it's not raining right now. Remaining 10% is carried by prevailing winds over the continent. So major water compartments. So the oceans obviously are going to be a massive source of water. Together, the oceans contain more than 97% of all liquid water in the world. The thing with that is that it's salt water. So you can't really drink it. Contains 90% of the world's living biomass. Yes, you have stuff in there like plankton, which is, but there's a lot of plankton, even though it's very tiny. But then you have whales, but there's very few whales. They moderate Earth's temperature. I think this is a big thing that people kind of forget, is that water has a very, very high specific heat. So it's very difficult to change the temperature of it. Therefore, people that live near large bodies of water, a lot of times they have pretty consistent temperatures year round. The Mediterranean is a good example of this. In a lot of places of Italy, especially near the ocean, the temperature is pretty consistent year round. Average resident time of water in the oceans is about 3,000 years. This means that if you track an individual molecule of water, it spends about 3,000 years in the oceans before it cycles out. Another one that's kind of overlooked is glacier ice and snow. I think it's been brought into the public eye recently with global warmings and the ice caps kind of releasing large icebergs that are then melting. So 2.4% of the world's water is classified as fresh, and 90% of that is in glaciers, ice caps, and snowfields. As recently as 18,000 years ago, 1/3 of continental landmass was covered by glacial ice sheets. And now Antarctic glaciers contain nearly 85% of all ice in the world. It's a pretty staggering statistic when you kind of think about it, that 85% of all the ice is located on one continent. Yeah, it's a big continent, but it's a lot. Sea ice comes from ocean waters, but salt is excluded during the freezing process. So groundwater, this is the second largest reservoir of fresh water. Infiltration is the process of water percolating through the soil and into fractures and permeable rock. So the zone of aeration is the upper soil layers that hold both air and water. Yes, air is a big component of soil. Zone of saturation, lower soil layer where all space is filled with water. This is where it forces air out. And then the water table is the top of the zone of saturation. You can look up the water table for your area. That information is published online. So here is a picture of it. You have transpiration from plants as they open their stomata, they release water. Then you have, of course, evaporation from land and water surfaces, precipitation bringing it back down, infiltration occurring as the water starts to make its way into the ground through percolation, runoff where it stays on the surface. Here's your zone of aeration where you have both water and air. Then you start to get down a little bit deeper. The soil starts to compress a bit more, and then you end up with your water table, and this is where your groundwater is. So in this, there is no air. It's just all soil and water, and that is the water table. So you can look it up for your area. Aquifers are porous layers of sand or gravel lying below the water table. Artesian are pressurized aquifer intersects, or where pressurized aquifers intersect the surface, so water can flow out of those without pumping. The recharge zone is the area where water infiltrates an aquifer. Recharge rates, though, are pretty slow. This is something that you can look up too, is the recharge rate. Presently, groundwater is being removed faster than it can be replenished in many areas. This is due to a lot of industrialization. Like if you have a well, those are private residents are going to be the first ones to feel it because they have a well, and that well usually goes just a little bit below where the groundwater table is. So here is where it's recharged, and you can see if you've taken any physics class, you know that in order for water to balance out, it has to be equal. Because the water zone is above where this well comes out, this pressure is going to cause the water to kind of spew out of this area. I don't know of any such examples of it. Major water compartments, rivers and streams. Precipitation that does not evaporate or infiltrate into the ground runs off to the surface back toward the sea. Best measure of water volume carried by a river is called the discharge. The amount of water that passes a fixed point at a given amount of time. This is something that is measured. You can measure it by looking at the profile of the riverbed and the walls of the river, get a profile of it, and then estimate how much water passes through there, and then doing some quick maths, you can figure out how much or what the discharge rate is. Usually expressed as cubic feet per second. Lakes and ponds. Ponds are generally considered small bodies of water shallow enough for rooted plants to grow over most of the bottom. Lakes are inland depressions that hold freestanding fresh water year-round. Both ponds and lakes are... whoever wrote this PowerPoint needs to brush themselves up. Both ponds and lakes will eventually fill with sediment and be emptied by an outlet stream. Looking at wetlands, I did some research in wetlands, so they play a vital role in the hydrological cycle. Lush plant growth stabilizes the soil and slows surface runoff, allowing more aquifer infiltration. Disturbance reduces natural water absorbing capacity, resulting in floods and erosions in wet periods and less water flow the rest of the year. A lot of times they're referred to as the kidneys of the hydrological cycle because they do a lot of filtration. The atmosphere, it's among the smallest water reserves or reservoirs. It contains less than 1/1000% of total water supply. Has the most rapid turnover rate though. This is with evaporation and rain. Provides a mechanism for disturbing fresh water over land masses and replenishing terrestrial reservoirs. So looking at water availability and use, renewable water supplies, it's made up of surface water or surface runoff and infiltration into accessible freshwater aquifers. About 2/3 of water carried in rivers and streams annually occurs in seasonal floods too large or violent to be stored effectively for human use. This is kind of key to it of why many places do not have hydroelectrical services. Rapidly accessible and renewable supplies are about 400,000 gallons per person per year. So looking at drought, every continent has a region of scarce rainfall due to topographic effects of or wind currents. Water shortages have most severe effects in semi-arid zones where moisture availability is a critical factor in plant and animal distribution. The U.S. Seems to have about a 30-year drought cycle. We just went through ours. Well, just went through it. It was quite a few years back. Climate changes such as global warming can alter these cycles. The Dust Bowl was kind of a major one. And these drought cycles, they range in intensity. It's not saying that they're all equal or they're all the same. Sorry, I had adjusted my chair. Withdrawal is the total amount of water taken from a source. Consumption is a fraction of withdrawn, or the fraction of withdrawn water made unavailable for other purposes. So basically it's not returned to the source. So you could think if you have 20 that's withdrawn and 18 that's returned back to the source, 2 is used as consumption. Degradation is change in water quality due to contamination, making it unsuitable for desired use. So that is a form of consumption where you basically make a water source unusable. Worldwide, humans withdraw about 10% of the total annual renewable supply. Many societies have always treated water as an inexhaustible resource. Natural cleansing and renewing functions of hydrological cycle do not work properly if systems are overloaded or damaged. So the damage is a big part of it, where we are destroying wetlands, but then on top of that, if we overload what wetlands are left, that can be pretty rough. Human water use has been increasing about twice as fast as population growth over the past century. The average amount of withdrawn worldwide is around 170,544 gallons per person per year. Annual renewable water supply in the U.S. Amounts to an average of 2.4 million gallons per person per year. Now withdrawal is 1/5 of this amount. So you can look at the total water use. Domestic use is what we use it for in our house. Industrial use is like in certain manufacturing processes where if you have to like water cool something. Agricultural use is used for farming, and then when you add all those up you get the total use, and you can see how that's increased over time. In agriculture, it's increased a fair bit. In industrial uses, it's also increased. Domestic use has increased, but notice how small it's kind of stayed, and that's because the purpose of water over time has kind of changed. So I was afraid I hit the wrong button on my keyboard. So water use by sector. Worldwide, agriculture claims about 69% of the total water withdrawal. In many developing countries, agriculture water use is extremely inefficient and highly consumptive. That's kind of the key to it, is it's inefficient, as in a lot of the water that's used doesn't actually end up helping the crops at all. Worldwide, industry counts for about 25% of its use. Water cooling for power plants is the single largest industrial use. Water cooling is where you take advantage of the high specific heat of water in order to discharge heat to the water and then remove that water from it and either cool it through radiators or just discharge that water. On my computer, I use water cooling on my computer, and it's basically a circulating pump. There's a giant radiator in the front of my case. It's 360 millimeters, which is 3 120 millimeter fans. And those fans blow on this radiator, cooling down the water that's inside the radiator. That water is then pumped to it's pumped to the CPU and the GPU, the central processing unit, and the graphics card, or the graphics processing unit, to cool those down, and then that hot water ends up going back to the radiator where it's pumped through and that heat is removed. Because of that, I can run my components a little bit harder, and it takes longer for them to heat up because they can discharge that heat off into the water easier. It also, the major advantage of it that I use it for, since I stream a lot, it's used to, because I can run my fans at the slowest speed and it'll keep it cool. Now, because I use a really quiet case, I have my fans running at its fastest speed, and I can hear them, but the microphone can't pick them up. It's too quiet for that, but I can hear them. But it's not super loud. Like, I have three, four, five, six, seven, 8, 9, 10 fans in my case, all running at full speed, and it's not all that loud. Like, it's, people claim that it's the loudest sound in the world. It's not really all that loud. Like when I'm wearing headphones, and I don't wear sealed headphones, it's completely quiet. So water cooling is a major thing that's used for that because of that efficiency that you can get out of it. Freshwater shortages. Estimated 1.5 billion people lack access to an adequate supply of drinking water. I always kind of think about this when I talk about this. I saw a meme where it was like the starving kid or whatever it is, where he's got this like questionable look to this like aid worker, and he was like, "So you pee into fresh water and then flush that fresh water down, or you put solid fresh water into fresh water in order to cool it down." So it's kind of that whole thing of, putting society into, the different socioeconomic regions. Nearly 3 billion lack acceptable sanitation. A country where consumption exceeds more than 20% of available renewable supplies is considered vulnerable to water stress. Globally, water supplies are abundant, but along with capital resources are unevenly distributed. What this is saying is that some people have access to water and then they don't use that, but what that does is it takes away water access to people who really need it. Currently, 45 countries, most in Africa or the Middle East, are considered to have serious water stress and cannot meet the minimum essential water requirements for their citizens. More than 2/3 of world's households have to retrieve water from outside of the home. That means that they do not have a centralized plumbing system in their house. And then, of course, sanitation levels decline when water is expensive. So groundwater in the U.S. is the source of nearly 40% of fresh water in the U.S. On a local level, withdrawing water faster than it can be replenished leads to a cone of depression in the water table. On a broader scale, heavy pumping can deplete an aquifer. So an example of that is a Ogallala water aquifer. So this was used from mining non-renewable resources. They had pumped this aquifer dry. So here's an example. You pump this up. This resident now has a dry well because you have this cone of depression where water is kind of drawn up, and this water can't percolate back in and fill this fast enough, while this can just keep going down until it strikes bedrock. Withdrawing large amounts of groundwater in areas can result in porous formation and collapse, resulting in subsidence. So basically sinkholes. Sinkholes form when these collapse. Saltwater intrusion can occur along these coastlines where overuse of freshwater reservoirs draw the water table low enough to allow saltwater to intrude. Sorry, my dog just made a noise. So here's an example, and I have a funny story about this. So saltwater kind of moves in as freshwater lends its depletion. Saltwater seeps upwards, so now you have this area of saltwater that's near your freshwater. So when I was in the Navy, we were doing some beach ops, which is where we would move ashore from a ship and then take control of the beach and then set up and establish a camp. We ended up digging. We were bored, right? Because we're stuck out there for like 3 weeks. I think we were out there and then something happened to the ship that we were on and they were rerouted. And so we were stuck out on this beach for 3 weeks. And this one guy I worked with, AJ, decided, I'm going to dig a deep hole in the ground. So he just started, it was like him and 2 or 3 other people just dug this real deep hole. And eventually they hit water because we're on the beach, right? So it's not like he dug like 4 miles deep. I think it was like, I remember a guy stood in it and then they buried him and he was like a little over waist deep. It was like torso deep. And the guy was a little bit shorter than me. So it was probably, if I had to guess, it was like a 4-foot hole, right? So there's this 4-foot hole in the ground and there's water in it. And I remember our OIC was like, I wonder if that's fresh water. And AJ dips his hand down, gets a handful of water and drinks it. And he's like, oh yeah, that's fresh water. And we were maybe like 50 meters at the most from the beach or from the ocean. And it was it filtered out all of the stuff like that quickly. I'm sure there was a salt level, but it was just so low that it was imperceivable. But it was pretty crazy, like how fast that the removal of salt is done. So increasing water supply, seeding clouds. This is where we try to form a condensation nuclei. Towing icebergs is another thing. Like you just find an iceberg and you go onto it and you drill, metal rods into it and you just drag those to where it needs to go. This is expensive though. Obviously you have to take a ship up there to drag an iceberg. There's also desalinization. So the most common are distillation and reverse osmosis. One of the ships that I deployed on was the USS Nassau, and it used both. It uses a 3-stage flash type distiller and reverse osmosis. The flash type distiller was the fastest, but what it does is it causes a low air pressure. So it's a vacuum, and it causes the air or the water as it goes into there to flash or just evaporate instantaneously. And then when it does, it then condensates into a small storage tank, which is then the water's cleaned and made either to use as coolant for the ship or as as steam for the ship or for drinking water and things like that, food prep. And then reverse osmosis was rarely used. We only used that when the ship kind of approached max capacity. So when if we were on a ship, because we were a land-based command, if we were on board a ship, the ship was approaching capacity. So we had both distillation machines and all the reverse osmosis turned on. 3 to 4 times more expensive than other sources, though. It's at this point you have to gather the water from the ocean, transport it to where it needs to go, desalinate it, and then run it through water treatment. Compared to here where we have the river, we just run it through water treatment because it's already desalinized and it's right there. So dams, reservoirs, canals, and aqueducts common to trap excess water in areas of excess and transfer it to areas of deficit. This has an environmental cost. There's a video. It's a guy named Foresty Forrest, who's a mountain bike rider who ends up going to an area in or does a bike tour of the Southwest United States, and he sees kind of the results of what happens when they transferred water. It upsets the natural balance of the water system. There's also ecosystem losses. You've destroyed this habitat of wildlife. Especially with the reservoir size and the water quality. There's a ton of videos about this online. It's really interesting to look up. So like the one in LA, the LA reservoir, that one is one of my favorite ones, how they put these black spheres on the top of it in order to kind of take care of a lot of the issues they were having with it. It's a displacement of people. The Three Gorges Dam in China will force the relocation of over 1 million people. There's evaporation, leakage, and siltation. This is evaporative losses from Lake Mead, and Lake Powell on the Colorado River is about 1 cubic kilometer per year, which is around 264 billion gallons. And dams slow the water flow, allowing silt or nutrients to kind of drop out of that water. The rivers around here, people are like, oh, they're filthy. They're not filthy. We just have a muddy bottom, and so silt is stirred up quite a bit in our rivers here, and because of that, the water appears really cloudy and brown. But the water quality itself is pretty good because it's clear. It's there's not a whole lot of other stuff that's dissolved in it, and it's not a whole lot of dangerous bacteria. And then loss from free flowing rivers can also occur too. So water management or watershed management is really big. There's a professor at Purdue Fort Wayne, Bob Gillespie, who does a lot with watersheds. But a watershed is all the land drained by a stream or a river. Here in Fort Wayne, we have 2 watersheds, and the Grand McCulloch Ditch at Eagle Marsh is the division. Retaining vegetation and ground cover helps retard rainwater and lessens downstream flow. Additionally, retaining crop residue on fields reduces flooding and minimizes plowing. Forest cutting on steep slopes protects watersheds. So you can see there's a ton of stuff that you can do in order to kind of improve the quality of a watershed. with domestic conservation, estimates suggest many societies could save as much as half of the current domestic water use without great sacrifice or serious change in life cycle or lifestyle. Largest domestic use is toilet flushing. I'm not suggesting you do the whole, if it's yellow, let it mellow. If it's brown, flush it down. That's just kind of disgusting. But a small volume of waste in a large volume of water. This is why toilets have kind of gone toward like low flow or waterless. Significant amounts of water can be reclaimed and recycled. So purified sewage effluent. This is where we extract sewage from water and then we sell that sewage to farmers in the form of manure. In typical US toilets, 38%. Bathing is 31%. This depends on how long your bathing is. Laundry and dishes is 20%. Cooking or drinking and cooking is 6%. And then brushing teeth and other things like that or other hygiene stuff is 5%. Which when I first saw this, I was like, wow, that's a lot more than what I thought. And so like some of the things, if you let the water run the whole time you're brushing your teeth, or if you shave outside, like I shave in the shower, I could shave outside of the shower and just turn the water on, clean my razor, turn the water off, and then shave. And then, you know, rinse and repeat sort of thing. Another thing that we used to do in the Navy was turn the water on, get yourself wet, shut the water off, cover yourself in soap, turn the water on, rinse yourself off. That way, when you're soaping yourself up, that water's not being wasted. Especially, you know, one of the bases that I was on, we had to have water shipped in because we did not have access to fresh water ourselves. So price mechanisms and water policy through most of U.S. history, water policies have generally worked against conservation. In well-watered eastern states, water policy was based on riparian use rights, riparian being streams and rivers or areas next to water. So in drier western regions where water is often a limiting resource, water law is primarily based on prior appropriation rights. What this is saying is that if you live along the edge of a river, that's yours. And so a lot of times what'll happen is these laws have not kept up with the pace of what we need. Imagine if I had to go and get permission from my neighbor to use the water in that river for bathing or things like that. So that's kind of where a lot of this comes in. So it's the use it or lose it policy, as in if he's not using it, then eventually someone else will take it. In most federal reclamation projects, customers were only charged for immediate costs of water delivery. But because dam and distribution system costs were subsidized, growing recognition that water is a precious and finite resource has changed policy and encouraged conservation across the U.S. So knowing that we're limited in how much we have, charging a high proportion of real costs to users of public water projects have helped encourage conservation. In 1999, the Canadian government passed federal legislation banning any bulk water exports. Water's too precious to be treated like other commodities. So an example of this, if you look up Nestle, the company that makes bottled water, I know you're probably like, well, Nestle they don't make bottled water in my area. Look up how many companies Nestle owns with their bottled water, and literally what they're doing is they are bottling tap water and then charging you for that tap water. And so it's such a high amount, and I'm not even talking about the plastic waste or anything like that. It's just the ethics behind charging someone an extraordinary amount for 20 ounces of water when they could just get it. And people will claim like, oh, the water here tastes bad, bottled water tastes better. It's the exact same thing. And because of that, a lot of times they have dried up a lot of aquifers and underground water resources. So it's been a major topic of contention, especially with Nestle. The other thing is they withheld water during crisis. So some crisis happened and it's like, hey, you guys have all this excess water. And they're like, so what? It's ours. So it's just a lot of like really shady stuff that they've done. But if you look up a video by Nestle, it talks about why they're hated so much. So to summarize everything we've gone over, I know this is kind of a long one. We talked about the hydrological cycle, major water compartments, water availability and use, the types of water use, freshwater storage, how we've depleted groundwater, increasing water supplies, water management, conservation, and the price mechanisms behind that water management conservation. So here's a picture of this person who has to retrieve water from a well. And a lot of times, if you don't have a pumping mechanism, it's just digging a hole that's deep enough to get down to the groundwater and then lowering in some sort of container to bring that up to the surface. You can also see there is a slight amount of spillage that has happened. And in some places, this water is considered to be precious to do that. So that's it. We're at the end of the semester. Today's the last day. I'm going to be doing office hours. So stop over if you have any questions or you want to say goodbye. But that's pretty much all I have. I did get an email today about people that were going to be taking the late exams. It is one of those things that after tomorrow, though, I won't be available to answer questions for the exams, or I will have my email over the summer. So if you have any questions, if you need a letter of recommendation, anything like that, send me an email. It is possible for you guys to find my private email on the internet somewhere and get a hold of me. If it's something that's like super imperative, it shouldn't take too long for you guys to kind of find your way around the internet to get that. But if you need a letter of recommendation, if you need anything like that, if you need help with whatever, get a hold of me and let me know. School email, I will check every so often over the summer. But I won't be checking it daily. But after tomorrow, because tomorrow's our last kind of work day for teachers. Today's the last school day for students. Tomorrow's the last day for teachers. So because of that, or because of that last day thing, then, you know, it will be a lot more difficult to get a hold of me. So if you do need to get a hold of me, kind of look up those resources. But that is all I have for AP Environmental Science. I have been looking at some of the test scores that people submitted before, and you guys were doing pretty well on the test. People that took it serious, at least. There were some students that didn't, but you know, that's something to address at a different time. If you have any questions at all or you need anything, just let me know. But for everyone who's taking the AP Environmental Science exam, the late exam, good luck on that. If you have any questions, let me know. But it was great having you guys in the course, and I will, for the juniors, I will hopefully see you guys next year, and for the seniors, good luck in whatever your next endeavor is. But thank you for watching.